Hello, I'm Dr. Harper. This video is in Management of Operations, a lecture video in Statistical Process Control Charts. So let's bring up the notes. Now, Statistical Process Control is part of Statistical Quality Control, which is broken up into two branches, Statistical Process Control and Acceptance Sampling. And in turn, they are broken up into how you measure the different quality characteristics, either variables, which are continuous measurements, or attributes, which are discrete measurements. Now, acceptance sampling really is based on the statistical theory of test of hypothesis, and process control charts is based on the statistical theory of confidence intervals. We will not cover acceptance sampling in this lecture. In this lecture, we will just focus on process control charts, which is based on confidence intervals. So the concept here is you have a process, and the process could be a manufacturing process, could be a service process where you're producing products, or even producing a product could be a satisfied customer. Now, this product will have different types of quality characteristics, such as length or width or weight, or different kinds of measurements as far as durability is concerned, strength, and from your products, identify quality characteristics, and you pull off a sample of size n. And from that sample of size n, you can determine, is this good quality or poor quality? And that's what we'll look at here. If it's good quality, fine, send it to the customer. If it's bad quality, then you go back, and there's two different approaches. The first approach is the process control, which we will look at in this lecture. You'll examine the quality characteristic from a sample on a statistical process control chart and make an inference about the control of the process. So that goes back to the process and makes inferences on the process. Is it in control? Is it not in control? The second approach is acceptance sampling. You compare the quality characteristic from the sample with something called an acceptance number or a rejection number and make a decision about the lot. And so remember, you have a sample of size n from a lot, and you make an inference about the lot and saying, I'm going to reject it and not send it to the customer. When you reject it, then that opens up all different kinds of other decisions. Do you scrap it? Do you destroy it? Do you recycle it? What do you do? We're not going to cover that in this course. We're going to focus on process control charts where we are inferring the control of a process. And notice acceptance sampling really doesn't infer any control of the process. It just makes decisions on the actual lot before it's going to the customer. So that's the concept. So let's investigate statistical process control. The objective of a statistical process control chart is to measure a quality characteristic over time to infer the control of a process. Now, the procedure of a statistical process control chart is one. First, conduct an experiment. Well, in conducting the experiment, the first thing you do is define the quality characteristic. Is it the length of the product? Is it the weight of a product? Is it the strength of a product? Is it the performance of a product? You have a measurement that you are going to apply to a quality characteristic. So then you create an experimental design which defines your samples, your sample size, how you take the measurements, and then you determine the sample size for the experiment. Well, this sample size for the experiment will be important because the sample size for the experiment then is used in the drawing a random sample and estimating your parameters from the experiment. So these parameters you're estimating, these statistical parameters, is describing the quality characteristic process. That's the first step. The second step is construct your chart. Well, you determine a sample size for the chart, and the sample size for the chart can be different than the sample size for the experiment. And notice I underline them for emphasis. But then you're going to be determining the center line CL, upper control limit UCL, and lower control limit LCL. And the definition of the center line, upper control limit, and lower control limit is the center line is the mean of the quality characteristic, and there's where the parameters come in. The upper and lower control limit is the mean plus or minus 3 times the standard deviation of the mean of the quality characteristic. Again, there's where the parameters come in. We want to estimate the mean of the quality characteristic and the standard deviation of the mean. And that's what we'll be doing today in different charts. But once we have the chart, then we monitor production and infer the control of a process. But then that's just the process control charts. And the process control chart, remember, is part of statistical quality control. And we'll talk about quality control programs in this video a little, an introduction. Okay, so let's go on. Let's construct a simple process control chart just to show how this works. A very simple one. First, conduct the experiment. A quality characteristic that is assumed to follow a normal distribution is defined. And we won't be going to all the different types of definitions of the quality characteristic that we could be measuring. I mentioned a few examples. Let's just assume we have a quality characteristic and we're going to measure it. A random sample from an experiment resulted in these numbers, whatever they are. They could be length, they could be weight, 3, 4, 4, 5, 5, 6, 8. I rank ordered them for ease. Now the sample size is 8 because there's 8 numbers. The mean, which is the sum of the numbers divided by the sample size of 8, is 5. If you add all these up, divide by n is 5. The variance of x, or the variance of the each individual random variable, is the sum of the mean, sum of the x's minus the mean squared over n, and that turns out to be 2 if you do the arithmetic. Okay, but notice this is the variance of x. X is just the value, the random variable. But notice this dividing by n. Now, dividing by n really is the population variance of x. But this is just the variance of x. It's not the variance of the mean. Okay, but so now we have our mean, we have our sample size, we have our mean, we have our variance. Those are our parameters. Next, we construct a chart. Well, in this chart, the sample size for the chart, let's say N2 is 8. Well, in this case, the sample size for the experiment was 8. The sample size for the chart was 8. It's the same. It's not always the same. It's not always the same. But in this case, it is, just to keep it simple. The variance of the mean is the variance of x, which is 2, divided by N2, which is 8. So it's 2 over 8. And I want to distinguish between the variance of x and the variance of the mean of x. Because one's the variance of x, the other's the variance of sum of the x over n. So that's just the variance of x over n2, which is the sample size for the chart. The standard deviation of the mean is the square root of the variance of the mean, which is the square root of 2/8. So now we construct our chart. The center line is the mean, 5. We bring 5 down. The upper and lower control limit then is going to be the mean, which is 5, plus or minus 3 times the standard deviation of the mean, which is the square root of 2/8. So in this case, it's going to be 5 plus 1.5 is 6.5. 5 minus 1.5 is 3.5. So there's our control chart. It is the center line is 5. The upper control limit is 6.5. The lower control limit is 3.5. Now we monitor the production. And we monitor production to infer the control of the process. So here's a lower control limit of 3.5. There's a center line of 5. There's the upper control limit of 6.5. And now these right here represents our production samples of size 8 for the chart. Sample size 8. We take the mean and we plot it. So this is a simple process control chart of the mean. Now let's consider 4 control charts based on the type of measurement of the quality characteristic and how we measure the parameters. There's going to be 2 attributes characteristics, and that is a P chart and a C chart. A P is the proportion of an attribute quality characteristic. A C is a count of an attribute quality characteristic. And the variables is M and R. The M chart is the mean of a variable quality characteristic, and R is the range. of a variable quality characteristic. So let's look at these 4 charts in this video. P chart. The control of a proportion of a quality characteristic. The P chart is commonly used for the detection of an anomalous proportion of a given attribute characteristic from a known sample size within a service operation or manufactured product. The data are assumed to be drawn from a binomial probability distribution. The binomial distribution for this development is characterized by 3 conditions. 1, only 2 outcomes per trial. Well, what I mean by trial is that we're measuring something. When you measure, your sample size before was 8. When we take a measurement, well, the outcome of a measurement is not a length or value. It's 2 outcomes. Either one outcome or the other, up or down, good or bad, right or left, red or green, acceptable, unacceptable. There's only 2 outcomes for every trial, and a trial is a measurement. 2, constant proportion of success. Well, each trial you can identify or code once one of the outcomes as a success, the other a failure. And that's not always true, and usually they're very nominal. It's red and green or whatever, but we'll just call one a success and the other a failure just to keep that clear. Now, the proportion of a success every time you take a trial is constant. That doesn't change. The third condition is independent trials. Every time you make a trial, or you observe, or you draw a random variable value, that trial is independent of the next trial. In other words, the way you draw your random sample, it's not correlated, it's not coordinated, it's not biased. They're independent of one. They're not dependent. They're independent of one another. Okay. Consider the following results. So those are the conditions in order for a P chart based on a binomial probability distribution to be used. If they're satisfied, then we can use the P chart. So let's do it. Okay. Next is the experiment. Consider the following results of an experiment from a process assumed to be in control. Experimental design is 10 samples with a sample size of 5140. Okay, and there's our experimental design. We have 10 samples, and the sample size is 5140. Now, here comes some terminology. A sample here, the number of samples is 10. The sample size is the number of observations per sample. So the sample size is not the number of samples. The sample size is number of observations per sample. So be very careful with that language. Now, of each one of these observations, you have only 2 outcomes, success or failure. And let's call a success an attribute, whatever that is. Now, an attribute could be success, it could be acceptable, it could be meet standards, does not meet standards. It could be all different kinds of definitions we want to place on it. But let's suppose our attributes, this is how many attributes we have out of 5,140. So we add up all the attributes, we have 1040. We add up all the sample size, which is 51,400. So we have a total of that many attributes out of that number of observations in the experiment. So to estimate the parameter of the average proportion, we take P bar, which is 1080, divided by 51,400, and we have this average proportion of our attribute of 0.021011673. We can round that to 0.021, and we will, but the actual average is as many significant figures as you can carry in your calculations. So that's the first part, the experiment to determine the parameter. Now, second part, construct the chart. From the experiment, there's our average proportion. Now, we want to obtain the sample size for the chart, and again, the N2 is the sample size for the chart, 1285. So the idea of 1285 is that this the sample size for the for the experiment is 5140. A lot of times that sample size really based on cost of the experiment, how much accuracy you want in the experiment, how much precision you want in your experiment, how much variability you want to reduce in your experiment. So this really has experimental requirements. But when we come to the chart, sometimes the sample size for the chart is production requirements. That's how many we're going to measure. That's how many we can measure. That's how many we want to measure. So there are two different approaches to this. One is your experimental sample size. The other is your production sample size. So let's say that we have 1285. Now we want to estimate the standard deviation of the average proportion. Well, first of all, the average proportion, since this is a p-chart and we have p bar, then this will be the center line of the p-chart. And down here you can see the center line will be just p bar. And I rounded it to 0.021. But now we want to estimate the standard deviation of that average proportion of p bar. Well, from binomial theorem, the variance of the mean is p bar times 1 minus p bar divided by n2, the sample size. If we take the square root of the variance, we have the standard deviation of the variance. We have the standard deviation of the average proportion. So we plug and crank, and notice I'm rounding this to 0.021 of p bar times 1 minus 0.021 p bar divided by 1285. Do the arithmetic, and notice I have 0.00400099. Even though I represented the p bar with only 3 decimal places here, when you do the calculation, never use a rounded number in a calculation. Always use all the significant figures when you do a calculation. If you round, then that tolerance, the intolerance, begins to stack up, and what happens is this number could be put off quite a bit. Never round during computation. Only round the presentation of a number, but use all the significant figures for the computation. Okay, now that we have it, now we can use the upper and lower control limit. P bar 0.021 plus or minus 3 times s 0.004. Again, I rounded to present the values, but I use all the significant figures to calculate them, and then I rounded again. So I've rounded it again. So there's these 3 values define the statistical process control chart to monitor future production. So let's do it. So let's monitor production now. Consider the production plotted for the P chart. The N is 1285. Actually, the N2 is 1285. Okay, where the lower control limit is 0.09, the center line is 021, the upper is 033, and there it is right there. Now these samples here of 1285 represent each sample. Now this sample, notice, has a sample size of 1285 because this is production. But up here, notice that this sample size is 5140 because this is the experiment. And that's why you have to keep them separate. Okay, so down here you have 1285. And again, it's 2 outcomes per trial. This one have the number of, we've measured the number of attributes on the first 15 samples. They're going to keep going. This is a timeline, a time series. And so now it's a P chart, so we're going to plot the proportion. So 28 divided by 1285 are this. So we get the proportion, and these numbers right here are plotted right here, and there they go. And there's my P chart, and it just keeps going and keeps going and keeps going. And this is the chart that we monitor our production to make sure that we do not have an anomaly that will indicate the possibility that we can infer the process being out of control. Okay, so that's how we construct the chart. Now, in the interpretation of the chart, now we'll say, okay, well, what we want to see here is just a random component. We want no other components other than just randomness. Okay, well then you'll have something called decision rules, are used to make inference about the control of a process. In other words, one decision rules might say, if all the values are above the line, well then, that if we observe that, then we are going to decide that we have an anomaly to infer the process is out of control. Use that as evidence to infer the process is out of control. Or suppose that it starts down here and has a nice linear line going up or a linear line going down. That's not random. So that would be used in the decision rule. We'll make a decision like that. It will be used as evidence to infer the process is out of control. So there's a number of different decision rules for each control chart, depending on the application, depending on what the quality characteristic is, and depending on what the quality objective is. Okay, but then once we have inferred that the process could be out of control, or it is out of control, then we move to something called the method of assignable cause. And that assigns anomalies in the control chart to causes in the process. Now right here is where you have the application of the process control charts. Because if you infer the process out of control, then that's the purpose or the objective of the process control chart. But you're not done. Because then you have to go back and say, if it's out of control, what's causing our process control to be out of control? And you try to assign anomalies in the chart to causes in the process. So that's how the process control chart is used within a quality program. And once you define it, then you go back and hopefully improve the process. That's where the process is improved. The process control chart really does not improve a process. It just evaluates a process, whether it's in control or out of control, as far as inference is concerned. If it infers a process out of control, the process control charts will not make it in control. You have to go back, find the cause, and improve the process. That is part of the quality control program. And there's 3 stages to a quality control program that I will present: quality planning, generating the chart; quality assurance, where you apply the chart, you measure production, you implement the decision rules, you have assignable causes, you decide what you need to do, and all that, assuring that your process control chart and all your measurements are applied correctly. And then finally, you have quality control, and I'm defining quality control as you're going back and improving the process. And so notice the process control chart is right in the middle of that quality control program in this 3-step process. You're planning to create the chart, you're assuring your measurements are correct by applying the chart, and then quality control is improving the process by interpreting the chart. And so all 3 of these need to exist. Now, other companies, some people call this QC, quality control. Some people call it QA, quality assurance. Some people say QA, QC. Some people just say, people say all different things. Whatever you call it, somewhere there has to be planning, there has to be assurance that your plan is applied correctly, and then you have to go back and actually improve the process. So whatever you call it, those 3 steps have to happen. Let's continue on. Once the experiment has been performed, and what's the purpose of the experiment? To estimate the parameters. Well, the parameter does not change, because that is saying this is what our process is doing. But different control charts can be constructed for different sample sizes using the same parameter. Now remember, the sample size is for the chart. Consider the examples below where the parameter P is from the experiment and a sample size N is given. Okay, so I'm changing N here. So for this N, let's assume we have different N's. Okay, let's bring this down and make this N2 again. And let's make this N2. Different values these are sample sizes for the chart. Okay, so the P's don't change. Okay, so now we say, well, when we have a sample size for the charts, well, notice the sample size here, and let's put a 2 there. This sample size for the chart is the sample size here for the chart is part of the actual standard deviation of the mean. So therefore, as the sample size increases, notice what happens here at 39, 38, 37, 35. The standard deviation decreases because the sample size is in the denominator. The center line doesn't change. So the center line stays the same, but the standard deviation decreases. So what happens is your chart will get smaller and smaller, decrease in width. And right here I'm demonstrating that. So 93, 96, 99, 105. So this is increasing the lower. The upper, 23, 22, 22, 21 is decreasing. Okay, and the center line here, 327, 24, 21, 15. This is decreasing. So notice that the size here, I took the upper control limit minus the lower control limit to emphasize the size is decreasing. So for the P chart, the center line doesn't change. But when the sample size changes, the chart gets smaller. So the concept there is you're measuring a proportion. When you have a larger sample size, then the actual proportion of that sample size should start getting smaller because you're measuring larger amounts of data. So the proportion should be decreasing. So the concept here is that so from now we can see what the concept is in the process control charts. In the experiment, we assume the process is in control. If it's in control, then this is what the proportion of our attribute should be when it's in control. So we use that to control it, to generate a chart. And then down here, this chart then is these numbers here are based on that experiment. But then when we start measuring proportions, we're measuring proportions based on this sample size. And these sample size then are plotted on the chart. So when the process is in control, then we should see a nice randomness of our chart. But if our process is out of control, then what happens is then that will infer that, then the chart will have anomalies that we can use as evidence to infer the process is out of control. Now notice I keep saying evidence to infer because it doesn't prove it. It's just evidence to make an inference. Because the process may be in control. What's wrong is your measurements. Your measurements, the quality assurance may be wrong, not the process. Or you've plotted it wrong, or you're measuring it wrong, or you have a wrong sample size. So there's a lot of different reasons why you'll have anomalies in charts. But when you do, that's evidence to infer. But then you have to go back and make sure that it's true with method of assignable cause, or make sure that you find a cause with a method of assignable cause. And that's beyond this course, this course. Okay, so let's go on. Closely related to the P chart is the C chart. And this is the control of a count of a quality characteristic. Now the experiment. The C chart is commonly used for the detection of an anomalous count or frequency of a given attribute characteristic from a service operation and manufactured product. The data are assumed to be drawn from a Poisson distribution. The Poisson distribution is characterized by a small probability of occurrence of an event in a defined interval of consideration. So there's the definition of a Poisson distribution. Let's back up. Well, from the P chart, let's suppose that you're using a P chart and the probability of occurrence happens. You have anomalies. You find the causes. you improve the process, and you keep improving the process. As you improve the process, the number of occurrences of negative events will decrease. So the interval of consideration is how many items you're measuring. And so in that, if the probability decreases, then the proportion of your attribute gets smaller and smaller and smaller if you're measuring errors, for example. So as you're getting better, the proportion gets smaller, then all of a sudden you're moving away from the binomial distribution to the Poisson distribution. When the proportion of a binomial distribution is small and the sample size is large enough, the Poisson distribution is a good approximation. And let me just mention here briefly, in passing, that in mathematics and mathematical statistics, you can take a binomial distribution and in the limit where the proportion p in the limit goes to 0, the sample size goes to infinity, then the binomial distribution will asymptotically approach a Poisson distribution. But that's in mathematical statistics. Okay, so that's when we're using it. So let's do it. Consider the following results of an experiment from a process assumed to be in control again, where the experimental design is 20 samples with a sample size of 1,000. Okay, now the 20 samples, each sample has 1,000 measurements in it. Okay, and so now I'm just giving you the samples here. Okay, but each sample will have 1,000 measurements in it. So now we're measuring a lot here. There's 20 samples, we have 20,000 measurements. That's quite a bit. Okay, now we're measuring the attribute in each one of these samples. Okay, and there they are. We add them up. There's 15 here, there's 25 here. Now to estimate the parameter of the average proportion, we take the total number of attributes, 15 plus 25, divided by the number of samples, which is 20, times the sample size of 1,000, and the estimate turns out to be 0.002, or as we see here, 0.2%, 0.002. So it's very, very small. Well, that's what we said before. If you remember, when the proportion gets really small for a binomial, then the Poisson is a good approximation. Well, this is small enough. This is small enough to move from a binomial assumption to a Poisson assumption. Therefore, usually you move from a P chart to the C chart, and that's when you change. Next, we construct the chart. Now, from the experiment, we have this proportion again, and we have 0.002. Now, that's the average proportion. We're constructing the chart for a C chart, so we want the average count. Well, we acquire the sample size for the chart. N2 is 850. Now, remember, we acquire it. This is the sample size for the chart based on production. And then now we estimate the average count per sample. But since that's our sample, and that's the proportion of our attribute in the sample, that's a proportion in the sample, or the probability that each observation is an attribute, then essentially what we do is we take the sample size times p bar, and that's going to be our average count, 1.7. So on the average, if we measure 850, then on the average, 850, 850, 850, a very large sample of samples of 850, on the average, the number of counts will be 1.7 per sample. Then we estimate the standard deviation of the average count. What's the standard deviation of C bar? Well, here we have a very nice property from the Poisson distribution. The Poisson distribution, the variance is the same as the mean. For the random variable x, if x follows a Poisson distribution, then the mean and the variance turns out to be the same number. Again, you could take the variance, p times 1 minus p over n, and in the limit, then you can show that the mean and the variance come together. Okay, so we just take the square root of 1.7. Again, we have, there's the standard deviation. And then we put them together just like we did before. The center line is 1.7. The upper and lower control limit here is C bar plus or minus 3 times S. And S up here is approximately 1.3. But notice what happens. When we do the arithmetic, the upper control limit is 5 point, well, that big number. I'm rounding down to 5.6. But for the lower control limit, it turns out to be a negative number. Well, in the C chart and the P chart and the R chart, which we'll do in here, you never report negative numbers as limits. You can't have a negative count. The minimum count is 0. So we round this to 5.6. We always round negative numbers to 0 for the C chart. But we also round negative numbers to 0 for the P chart. We also round negative numbers to 0 for the R chart, which we're getting ready to do. But we'll do that automatically. So now that we have the chart, these values then define the statistical process control chart to monitor future production. So let's do it. Here's where monitoring production. Here's our N2. Again, let's take the N2 because that's the sample size for the chart. And down here, we're going to plot it. Here's our lower control limit, center line upper control limit. Here's our 850, our sample size. That's the attributes. Now this time, all we're plotting are just the attributes, just the count. And there they are. Okay, but notice this time we have an asymmetric chart. Asymmetric because we rounded to 0, which is essentially truncating all the negative numbers up to 0. We eliminate those because it doesn't have any real value, real interpretation. So we round up to 0. But notice we have 3 numbers here that are right on that line. So if it's on the line, is it in or is it out? Well, when it's on the line, it's in. Okay, like up here, this is 5.6 up here and this is 5. But so when you're doing a count, they're integer. You'll either have a 5 or you'll have a 6. 5 is in, 6 is out. Okay, but down here, 3 of them are on the line. If they're on the line, then that's interpreted to be in. Okay, not out. So we have an asymmetric control chart, and if the points are on the line, then they're defined to be in. So this is random component, or is it? Well, there's where the decision rules come in again. There's where the method of assignable calls comes in again, and the quality control, the 3-step process of the quality control program comes in. Same application, just like we did with the P chart. Okay. Same process, same everything. Okay, now for the C chart, once the experiment has been performed, the parameter does not change. But different control charts may be constructed for different sample sizes using the same parameter. Consider the examples below where the parameter P is from the experiment and the sample size N2, again, let's make that N2, is given. And down here's the N2. This time when this goes up, notice N is part of the center line. The center line gets larger. So remember with the P chart, the center line didn't change. But with the C chart, if the sample size goes up, the center line, the actually control chart increases. So it actually gets larger. But the center line is also part of the variance. Well, the center line is the variance, and the square root of that is your standard deviation. So therefore, not only does the chart increase, but notice that the chart will grow in size as well, or the interval will grow as well. And notice here for small sample sizes here, the minus is rounded to 0, and these numbers then you kick into the numbers. And so each of these keep getting bigger and bigger. So this is the lower control limit. There's a upper control limit, And notice 4, 5, 11, 19, 22. So as the sample size gets large for the C chart, the chart increases and the size of the chart increases. Because we're not dividing by n, we're counting. So when you're counting a larger sample, you're going to count more. So you're going to have a larger number. And so the same probability or the same likelihood of being in control or out of control, the interval needs to be larger. And that's how these charts are used correctly. Okay, let's go on. The last two charts we'll look at is the M and R chart, the mean and range of a quality characteristic. First, the experiment. The M and R charts are used to detect the anomaly in the mean and range of a given variable characteristic from a service operation or a manufactured product. These two charts are usually used together. The data are assumed to be drawn from a normal distribution. The M chart is also called the X bar, or X with a bar over it, chart, which means the sample mean. I'm using M because it's easier. M bar, mean. It's easier just to represent it. Consider the results of an experiment from a process assumed to be in control. Now, this is going to be a little bit different than the other two. My experimental design is 10 samples with a sample size of 4. And notice, every single one of these, my experimental design is made up of two things. One, the number of samples, and two, the sample size. So those two pieces of information define the experimental design. Okay? Well, so here I have 10 samples, and there they are. Here I have the sample size is 4 measurements. But in this case, notice what I do. I actually list the actual measurements. Okay? And let's suppose these measurements are, let's say, length of millimeters, for example. And so what are the parameters? Well, if you notice in the P chart, our parameter was P bar. In the C chart, our parameter was P bar. Same. But for the M and R chart, now there are 3 parameters. And over here, the 3 parameters simply are the sample size, the grand mean, and the average range. Well, let's see what those mean. First of all, the sample size n equals 4 is, again, the sample size in the chart. Whoops. Do this again. So the sample size in the chart, the sample size of the chart is a parameter. I'll show you why in a minute. So that is something we need to pull down. So that's not going to change. So now the sample size for the chart will also be the sample size for the sample size in the experiment will also be the sample size for the chart. So let's just say here n is going to equal n2. So that becomes a parameter. Sample size for the experiment becomes a sample size for the chart. Well, the second parameter is, I call it the grand mean, m bar, which is the average of just all of the measurements in the experiment. Okay, there's 10 samples, 4 measurements, there's 40 numbers. You average all 40 of them, and the average, you sum it all up, 6160 divided by 40, 154 then. That becomes the grand mean, or the average of everything in the experiment. I call that m bar because that's the center line of the M chart. The third parameter is the average range. So now we need to get the range for every sample here. Well, a range of a sample is simply the difference between the maximum and minimum value. So for this case here, the maximum value is 194. Okay, let's get the sample. The maximum value of those 4 numbers is 194. And there it is. The minimum value is 110. Well, 194 minus 110 is 84, and that becomes the range of sample 1. We do that for every sample. For sample 2, let's see, what is it? Let's see, 192. The minimum is, 130. 192 minus 130 is 62. So we do that for every single sample. and then we sum the ranges, divide by the number in the sum, and that's my average range R bar, and that will become the center line of the R chart. Okay, so there's our three parameters: the sample size of the experiment and the chart, the grand mean from the experiment, average range from the experiment. Okay, so let's construct the chart. So now when we construct the chart, this is a little different than we've done before. On here, here we have the M chart, and here we have the R chart. Here we have the center line. Well, the center line is easy. I just copied this from our parameters up here. The grand mean of 154, the average range of 70, I just copied them right here. And there they are. Now, the upper control limit. Let's start with the M chart. Let me just highlight this right here and say, remember the definition of an upper control limit is M bar plus 3 standard deviations of M bar. That's the definition. But we don't have standard deviation as a measurement of variability. Instead, we have the range as a measurement of variability. And that is a measure of dispersion, of variability, or dispersion. So instead of M bar, we want to use R bar, because that's what we have available. Okay, and so if it's R bar, then we still want to define 3 standard deviations of M bar, because that's the definition. So the question arises, if we're using R bar instead of standard deviations of M bar, then what do we multiply R bar by in order for that number to estimate 3 standard deviations of M bar? Well, this A2 is a coefficient, and that coefficient was determined years ago, decades ago, and it's very common. It still can be used today, and it still is used today. And the value of A2 is in manuals that are published, etc. Now, what I did down here below is actually have an excerpt of some of those manuals, and they're very, very old. Well, very old. I think they did it in late 40s, early 50s of last century. And so, how do we know which here's a bunch of A2s? Which one do we pick? Well, there's where the sample size comes in. Where n is 4, the variable that we pick, the coefficient that we pick, is from the sample size n equals 4. So A2 then will be 0.729. So I bring up 0.729 for A2. M bar is 154. R bar is 70. I do the arithmetic, and there's my upper control limit. And so these tables down here will be given, okay? And then the lower control limit is the same numbers, except we change the plus to a minus sign. Same logic. So there's our upper control limit. There's a lower control limit with a center line. So there's our M chart right there. Okay. Now the R chart. Same logic. Same logic. Here is the R bar is our quality characteristic plus 3 times the standard deviation of R bar. Well, R bar is a measure of variability or dispersion. So we have a measure of variability in the center line here, the mean, but also standard deviation of R bar is another measure of variability. Okay, so actually when you have a random variable, and that random variable could be a mean or variability or variance, but that's a random variable because every time you take a sample, the range varies, the standard deviation varies, but then that value is a random variable. Well, every random variable, almost every random variable that we look at, will have a mean and a variance. So the sample variance varies, therefore it has a variance. So, but that goes a little bit beyond this course. But the idea is that that's a measure of variability, but the R bar is also a measure of variability. So then they say, okay, well, instead of just doing this twice, what do we multiply R bar by in order for this whole number to represent R bar plus 3 standard deviations of R bar? How do we do the whole thing? Well, again, the D4 comes from a sample size of 4. And that's why the sample size is a parameter, because the sample size of 4 is being used for the M chart, R chart, and the coefficients. Well, first of all, D4 over here is 2.82. I bring this up, 2.82 times R bar, which is 70, and there's my upper control limit. I do the same thing for the lower control limit, but this time it's D3. D3 is 0. Notice when the sample size is small, instead of having a negative number there, it's going to be 0. They've already truncated or replaced it to 0, because you can't have a negative range. You're not allowed to have a negative range. It's undefined in this application. So therefore, it's just 0. So here's an example of just the lower limit being 0. So you would never, in this course and in most industries, you never report a negative number for an R chart, a P chart, or a C chart. Okay, now that we have our charts, now we can monitor production, and here they are. And so we consider the measurement from the production plot on the control charts, and there's our sample size of 4. And this time we have 15 measurements again, and there's all of our measurements down there. For each sample, we calculate a mean, M bar, and an R bar. Okay? Actually, this would be an M bar and an R bar. And down here, we plot the M chart here. So all of these numbers are plotted here. And all of these numbers are plotted down here. Bing, bing, bing. And so there's our chart. And usually these two charts are used together. Okay? Because the M chart usually is a measure of central tendency. Okay? And the R chart is a measure of variability. Okay? And usually central tendency has to do with measurement of bias. Is it really biased? This is what you should be measuring, but there's a bias. And the R chart usually is a measure of consistency or reliability. Is it repeatable? Okay, so these two charts are usually used together to measure bias up here or reliability down here. Okay, and so these right here, let's come up here. Let's go ahead and do this. R bar, M bar, and then R bar. And there it is. And so each of those are M bar and R bar. Okay, and there we have it. Okay, and so that's going to be the 4 control charts we'll look at here. Now, granted, there's a lot more charts than just these 4. Let's come back to the beginning. There's a lot more charts than just these 4. Okay, and sometimes you just want a simple chart, a real simple one like this. And process control chart can be used by companies, can be used by individuals. It can be used with just your normal individual's progress report. And people can use it individually because it's very simple, very effective. You have a timeline, a time series plot of your performance, or you can monitor things over time. So it's very valuable and very useful. Okay, that's all I have for this lecture. I hope this helps, and between now and the next time I see you, I'm going to urge everyone to be very safe and take care.